Alright, so we should be live. Let me get the audio fixed. Okay, so audio's good, and I think we're up. Okay, so let me open up this PDF, and that's going to be kind of where we go from here. Just open that. Okay, so what I'm going to do is I'm going to put, I'm going to actually split screen here. So let's see if I can do that with OBS and not have it uncooperative. Okay, so you should be able to see two things on the screen. On the left, you should see the the notes, and on the right, we're going to go to Joel's Brookshire emulator, which we were looking at last time. Okay, so does it look like we're actually getting these on, or did I accidentally switch inputs on OBS? Laptop display capture. Okay, I'm not sure if it's actually showing up. Well, crap. Okay, well, let me just do this way then. We'll just go back and forth. And so let me just set up a window capture to preview. Here we go. Okay, we'll just do it this way then. Okay, so you should be able to see here the notes. And I'll have to switch back and forth between this and Safari, which is annoying, but whatever. Actually, no, I don't. What am I doing? I'm being an idiot here. Let's do Safari, and we'll just switch back and forth this way. Okay. All right. So let's just recap what we had. The basic machine architecture that we're going to sort of play with is, well, right in front of us. It has, like I said, a whopping 256 bytes of memory. Wow. And it has 16 of these special memory cells called registers that are inside the processor. Every processor has some of these, and how many and what they're called and stuff just depends on the architecture. So, like classic Intel architecture basically had like 4, and they were called A, B, C, and D. Makes sense. More modern architectures have some more of these things. So, for example, your smartphones are all running 64-bit ARM architecture. Those have 32 of these sort of general purpose ones. They also have another 32 ones for floating point, like math computations. Okay, so the way that this is going to work is, so there's two ways that, well, let me back up. There's two ways that we could theoretically set up a computer, okay, in terms of what we put in memory. Because what things need to go in memory? Well, instructions for what to do, right? And also data that you're going to do stuff with, right? I mean, what else would we have? Okay, so the question then is, how should we organize those things? Could we have two separate chunks of memory, and we'll put instructions in one and data in the other? We could do that. Okay, that's called a Harvard architecture. And there are older machines that would use stuff like that. Okay. There's also what's you could just have one pile of memory that would be used for storing both instructions and data, and then you only have one piece of memory. You know, they're not two separate things. Such an architecture is called a von Neumann architecture, and that's the kind that basically most computers nowadays are. Right? You've got one big pile of memory, gets carved up in a few different ways, but uh, you just have memory. That's it. The second one, von Neumann, um, after the mathematician, and it's Neumann, I think. Um, yeah, and then the other one's named after Harvard, obviously. Um, so our architecture, data and instructions will go in memory, and we have, like I said, exactly 256 bytes worth of it. So we're not going to be programming Minecraft or anything like that on here. Um, there's not nearly enough memory to contain all of that stuff. Okay, so um, so let's see what we can do with this thing. Well, first off, we need to know what are the instructions for it. Okay, now last time I pulled up and I wrote just a simple little program in C. And, well, first I wrote it in Python, and then I basically translated and wrote the exact same thing in C, and then did some voodoo, and weird code appeared, right? And so we started looking at that weird code. Um, in that weird code, there were lots and lots of different instructions, and each one does precisely one thing. Um, and each program is just a series of these very basic instructions, okay, on the lowest level. So if you wanted to know what the instruction set is for, say, a modern processor, get ready to read a manual that's like several hundred pages thick. Okay, there's, excuse me, lots and lots of instructions, and therefore, um, you've got a lot of details to read. The architecture that we're going to work with has 12. That's it. Okay, and 11 of them are really easy. Okay, so we'll talk about this circuit stuff later. Okay, so here are our 12 instructions. Okay, and what the book made up is basically the column that says opcode, and then the rest of it, well, and the description, okay? What I did was I made up the stuff in the middle, which will be the assembly language. So let's just make sure that we're clear, right? High level language like C is more human readable, but still looks like code. Okay, assembly is one layer below that, still human readable, but not nearly as much as Python or C. And then at the very bottom, you've got the machine code, which is just all the ones and zeros and stuff. Okay. Okay. So what are our instructions? Well, what can we do? We can move data from one place to another. So we have here two different load instructions. So read them there, right? First one is load a register with the contents of a memory cell something. Okay. The other one is load a register with a bit pattern something. Okay, and I've used here X and Y to just sort of represent whatever. Okay, um, so two things to notice. What's the difference between those two operations, both in terms of what they do and how they're written? Yeah? Yeah, okay, there's something going on with pound sign versus dollar sign. Okay, and I was very deliberate there. Dollar sign XY refers to memory addresses. Okay, so the dollar sign tells you that what that thing is talking about is a memory address, uh, something. So, for example, memory address 2F or whatever. Okay. The hashtag is used for talking about specific numbers. Okay, so immediate, we call those immediates. Okay, so specific numbers. So if I want to load the actual number 2 into a register, there's two things I need to do. One is in my assembly, I would write load register number and then the pound sign with whatever number I want to load. Okay, whereas the first operation is going to go to memory cell number 2, and whatever it finds there, it's going to copy that into a register. Okay, so you guys see the distinction? It's loading a specific number versus loading whatever happens to be in memory. Okay? Okay. All right, well, if I can take things from memory into a register, I ought to be able to go the opposite direction, right? And take something from a register and put it out into memory. That makes sense, right? So that's opcode number 3, is to take the contents of a register and store them to some memory address. Okay? We can copy data from one register to another. Now, the book calls this the move operation, but really it's copy because, so what's the difference between a move and a copy? Yeah, exactly. So copy doesn't destroy the source. Move would. Okay, like truly, if this were moved. So I left it there called move because that's what it is in the book, and okay, but it's really copying. Um, and that you might say, well, why don't you just rename it copy? Because um, uh, real architectures still use move or some variant on that word. Okay, so my guys in the 241 class are doing, they've got their programs have F move all over the place because it's moving. Right now, they're writing floating point programs, so it's moving floating point data to and fro. Okay, great. So we can move things between registers. Okay, so those 4 operations are all about moving data from one place to another. Okay, in all the different sort of permutations for where it can come from and where could it go. You guys all know the song, right? Where did you come from? Where did you go? Can I, Joe? Okay, that's our humor for the morning because my head can't take any more of it. Okay, so now what other operations can we do with data? Well, we can do arithmetic or logical operations, and that's the next big pile of what it looks like 6 of them. Okay, we can add numbers as integers or as floats. Okay, and then let's look at the add I. So I there stands for integer. Okay, what is the order of the operands? Okay, so who gets added to whom, and where does the answer go? And I'll post this up to Canvas so you don't have to like surreptitiously take selfies. Yeah. Well, they teach you in Classroom Management 201, you learn advanced classroom surveillance techniques, right? Uh, yeah, reading stuff upside down, uh, noticing when students are texting. What else? Yeah, there is no such class, by the way. Do you guys know how much training I have actually had as a teacher? About 15 minutes. When I started graduate school, it was basically, all right, here's the textbook. Here's where you're supposed to show up and when. And you'll give a quiz every week and give it to the professor beforehand to make sure it looks okay. And see ya. Off you go. So, yeah, it's kind of scary, right? Yeah. Anyway, so we can do addition. So what's the order here? RST. What do you write first? The register number of where the answer goes. Okay, so in a lot of architectures, the destination is written first on these things. Why do we make it that way? I don't know. That's just the order, and that's a relatively standard thing on a lot of different architectures. So I just kept it that way. The other reason is that when we actually encode these instructions, they go in that order, and that's what the book said to do. So I didn't want to break that. Okay, so we could add as integers or add as floats. Then we have three logical operations, OR, AND, and XOR. Okay, and those work bitwise. So we'll look at examples of that later. I can also rotate a bit pattern, which is kind of like shifting the bits around. And again, we'll look at what that is. Okay, and then the last two instructions are, well, the second to last one is the most important one of all, because this is what makes this a computer and not a calculator. It's the ability to make a decision, and therefore we can do things like if something, then something else, otherwise some third thing. Okay, so the jump instruction. Okay, and what this will do is it will take a register and it will compare it to register 0. Well, the contents are either equal or they are not. What are the two? If they were equal, we will jump to a different place in memory and continue executing instructions found there. If they're not equal, then we will just move on to the next instruction. Okay? That's where that instruction is going to be the hardest one to understand, and therefore where we'll need to spend the most time. Okay, the easiest instruction to understand is the very last one, because it just turns everything off, right? So when you hit the end of a program, you should stop doing stuff, and we need an instruction to tell the processor to stop. Okay, so that's the halt command. Okay, does that kind of make sense? All right, so let's start writing some code here. So let's load some data into some registers. Okay, so what opcodes do I have here? 1RXY and 2RXY. So let me just write something. Let me do. Okay, so what I've written here are two instructions, 1102 and 2202. Okay, so what should they do? What does 1102 do? Let's go back to the sheet for reference. Okay, so 1102 is going to load register what? 1 with the contents of memory cell 02. Whatever is in memory cell 02 will get copied into the register. Is the contents of memory cell 02 the actual number 02? Maybe, maybe not. Okay, but the contents of the cell and the address of the cell are two different things, right? And maybe the best way to think about this is, well, I don't know how you fraternity guys do it, but the Jeeds, anyway, you go down to the basement of Sparks, and what do you guys see? Well, there's the mailroom, but there's all those little mailboxes, right? Okay, the mailboxes all have numbers on them. So let's say your mailbox number is 74. Well, if you open your mailbox number 74, what do you find in there? Well, really? You find mail in a mailbox? Shocking. No. Okay, but do you find the number 74? Probably not, right? The contents of the mailbox and the number that's on the door are not the same thing, right? And it's the same thing here, right? Each memory address can hold exactly one number. So it'd be as if all the mailboxes could hold a piece of paper that had a single number on it, and that's it. Okay? What number is inside the box isn't necessarily the same as what's on the door. Okay? Okay, so what about the second instruction? I picked 2202. Okay, so what's that one going to do? Right, load register 2 with the actual number 02. Okay, and all of these numbers, by the way, are in hex. Okay, so if you write 10, what really is that? One. 10. 16, because it's in hexadecimal. Not binary, hex. Right. Right, which is 16, right? Okay, I know it's early in the morning, and I'm not firing off 4 cylinders either. Like, I need a little bit of lead in my gasoline to get out the NOx. No, you guys don't get that anymore because we haven't put lead in gasoline in 50 years or something. Huh? Oh, that too. Yeah. I don't know. Lead-based paint was real tasty as a kid. I mean, yeah. Okay. All right. Anyway, so let's execute this and see what actually happens. And then the third instruction I put at the end was just a halt command, because otherwise it'll say illegal instruction. Okay. So here's how the processor is going to start executing things. This particular architecture, your program must start in address 00. That kind of makes sense. Where else would you want to start? Well, you could theoretically start anyway, but you have to start at the beginning of memory. Okay. And so what's going to happen is right now, what is the program counter? That's PC and the CPU. 00. Okay. So what that is going to do is the processor is going to load from memory the instruction that's found in memory addresses 00 and 01. Okay, so the program counter points to where the next instruction is to be loaded from. Okay, and on this particular architecture, every instruction takes 2 bytes worth of data. Okay, so the program counter will go up by 2 every time. Okay, so where's the first instruction that needs to get loaded? It starts at memory address 00 and finishes at memory address 01. So I need to copy that information into the instruction register. Okay, so I'll do that. And that is the fetch step. Okay, so right now the processor is sort of paused, if you will. Okay, so what got copied from memory into the IR, the instruction register? 1102, right? That was my first instruction. Okay? Well, now what? We have to figure out what the hell that means to do and then do it. Okay, so that would be the decode and execute stages of this, right? So the cycle for this will be fetch an instruction, figure out what it says to do it. Fetch the next instruction, figure out what it says to do it, and continue that procedure over and over again. Okay? All right, so what does 1102 mean? What did we say it meant? Take the memory address 02, whatever's there, copy it into register 1. Okay? All right. So, and that's what is there. So register 1 gets the contents of, and this is one thing about Joel's emulator that I need to do some reprogramming on. When he writes 0x02 with the parentheses and a star in front, he means memory address. Okay, I should change that so that it's dollar sign, and that way it's consistent with what we've already done. But his source code's on GitHub, and I've got a bucket list of things that I want to add to this thing. I've actually written to the guy. He was like surprised as hell that I was actually using it in teaching. And I'm like, oh yeah, it's great. The students love it, right? So anyway, he's in like which country is it's Scandinavia. I don't remember if it's Finland or Sweden or whatever, but he's over that way. Okay, so that's what the instruction says to do. Now we need to actually do it. Okay, so pay attention to register number 1 over there in the column on the left. Bam. Okay, what got put there? Were you expecting it to be O2? Are you going to live over there? You look like death. Why do you look like death? Oh. Speaking of death, how's Typhoid Terry? Uh-huh. How was it? Hmm. Has anybody else actually had it and had symptoms? No?
I did.
You did? Yeah.
Guy that I know from Delft is just like laying in bed. It's like, it's awful. So he actually has it.
Yeah. Well, it's all fake news. Yeah, fake news. All right. So how many of you guys were expecting to see the number 202, pop up in that register? Okay. So why were you expecting that? Because the instruction said 1102, right? Okay, but what does instruction 1 do? It says go to mailbox number 2, and whatever you find there, put it in register 1. Okay, what is in memory address 02? 22. Okay, does that make sense? Right, so I deliberately picked that to illustrate the difference. Well, because what is in memory address 02? Oh, okay, good question actually. So how do I read the memory addresses there? So you see there's a number on the down the side and there's a number across the top, right? You read it kind of like a multiplication table. So what's cell 00? That's the one in the top left. 01 is to the right of that, 02 to the right of that, and so on. So the so where is memory address C0? Yes, that's not exactly what, C0 is right here. C0, right? You sunk my battleship. Is that okay? Yeah. Is that really how it is in Battleship? I don't remember. It's been so long.
Well, that one it's
Across and then down?
it's letters and then numbers at the top.
Oh, right. Okay. But here um, it's numbers for both of them because it's all in hex, right? Well, okay. So maybe here's another way to think about that: is that the who gets written first and who is first in terms of lowest significant value are not the same thing, right? So, well, like, how many of you guys have done matrix algebra either in high school or taken linear algebra? Right? We say row first, then column, right? And that's exactly what we're doing here. I'm telling you which row is the box in, and then which column is it in. And that then tells you exactly which box to go to. Okay. Okay, but here's the other thing. If you went to the mailroom, how are the mailboxes? It's probably 1, 2, 3, 4, 5, 6, 7, 8, not 1, 2, 3, 4, 5, 6, 7, 8. Right? Okay, so our order is the formal order. Okay, so are we clear though that box number 02 has contents 22? Okay, good. All right, next. We just executed it, so the data appeared. All right, so now what? Do the whole thing over again. So what's my program counter this time? 02. So which box am I going to go to load in the next instruction? I'm going to go 02 to 03, okay? And that is the instruction 2202. Okay, so I've just fetched in that next instruction. Okay, now what? We need to decode it and then do what it says to do. All right, so fetch, decode, what does it say to do? Load register 2 with the actual number 02. Okay, so when I hit the next step and it goes to execute it, what should appear in register 2 over there? The actual number 02. And bam, there it is. Okay? And then the process continues. So what's the program counter? Excuse me, now? Well, 04 and 05 would be where the next instruction is, which is C000. All right, what does that say to do? Stop and execute terminates program execution. Yeah. This particular website, every computer, every processor, it's moving data to and fro, and then if we threw in more stuff, we would be adding it. Okay, so well, allow me to demonstrate. Well, it's more than just RAM, but yeah. All right, hang on a moment. Let me make sure that I'm actually transmitting this. Yes, okay. Oops. So, oh no, wait, I wrote it in C first. So I want to do AS, Arch1, no, GCC. That is not what I meant. Okay, so um, okay, so what I've done here, right, and I know this may be a little hard to read, is so in the little website, right, we have sort of a graphical display of all of the registers and their contents. And then also we have a display of memory and its contents. All right, now first off, I can't display all of memory because there's gigabytes worth of it here, and that won't fit on the screen. Now I can look at small segments of memory. Now that's no problem. Okay. All right. So we can look at the registers here, and what are they called? A, B, C, and D, with the R and the X. That's okay. Register R, AX, meaning it's a 64-bit wide thing. Okay, and I can see exactly what's inside there. What is inside that first register? Well, it's this giant hex number, which as an integer is all of that jazz. Okay, does that number mean anything to me? Not really yet. Okay, what's in register B? 0. Okay, what's in register C? Big number, right? And register D, another big number, and there's data, right, in these. And then some of these registers have like 0 and 1, or this one down here has some other stuff, and there's some special registers like this one called E flag, RIP, that's not RIP, that's instruction pointer. Um, okay, not RIP, yeah. Yeah, okay. Then so we've got all these different registers, and there's, you know, some of them have special names, right? So base pointer, stack pointer, 8, 9, 10, and so on. Then A, B, C, and D, those are still there because this processor that's, my fancy old i9 that was manufactured in 2020 or maybe 2019, right? Can still execute Intel code from the 70s. Okay. And classic Intel architecture from back then, okay, so the original like 8086, had 4 registers, A, B, C, and D. And then it had a few of these specialized ones. But, right, so what's nice here is that it is backwards compatible. And this is why you guys can run stuff. I mean, maybe not from the 70s you're running, but I don't know, maybe one of you has Oregon Trail on your computer, although maybe you guys are a little young for that. Did you guys ever play Oregon Trail in school? Okay. Yeah. Yeah. Yes, on a that but you're young enough you never had floppy floppies. You had hard floppies probably.
Yeah, we had the smaller ones.
Right. Okay. See, I remember the floppy floppies. 5 1/4, and you could shake them like a Polaroid picture. Yeah. No. Okay. All right. Anyway, so what we're looking at are the registers, kind of like in the Brookshire thing. Okay, I'm just using an actual. All right, now let me do, for example, let's look at some memory. Okay, so what I've done there is I've gone to a particular segment of memory, and I'm looking at what's there in memory. Okay, and the guys that are in CS241 are using this program called GDB to debug their programs and step through line by line and make sure that the data is getting moved from one place to another the way they intended it. And if something weird happens, they use this program to try and identify what's going wrong. Okay? So this is like the big boy version of Joel's emulator, right? Okay, so yeah. Now I should say, just this looks slightly different to the guys in the architecture class because we're doing it for ARM architecture, not Intel, but the same idea. Okay, I can't emulate GDB on a non-ARM computer. I'd have to do it live on the actual like Raspberry Pi to do it. Okay, but that's what we're up to. Okay, is this level thing, but we're not doing it for a real processor. We're doing it for the made-up one because the made-up one is a hell of a lot simpler. Okay. Okay, does that make sense? Let me go back to Safari. Okay, so basically our machine as simple as it seems, is powerful enough to do pretty much anything except recursion, which is annoying, but oh well. That's also in my bucket list, is to extend it a little bit so that it can do recursion. But I'd have to modify things quite a bit. Um, the other thing I really want to do is, uh, this processor doesn't exist in physical form. It's purely a sort of intellectual construct. So what does that mean I want to do? I want to build one, okay, and put a bunch of chips and stuff together to actually build this thing, because I think that'd be cool, right? Actually, what would be really cool is then to have like a punch card reader, and you have to write your program on punch cards and then load the punch card into the reader, and then it would transfer the data into the machine and execute your program. Huh?
That'd be cool.
It would be cool. So when you said that'd be sick, it's sick in both meanings of the word, right? The slang meaning and meaning that'd be really cool, but also like my dad tells me stories of carrying the stack of punch cards that's maybe 3 inches tall, to the mainframe in the library or whatever, and you hand your stack to an employee and they put it in the thing, and you come back a few hours later and you get a printout with what your program did, which usually is error, and you have to then figure out what the heck you screwed up on your punch cards. And heaven help you if you drop them between your dorm room and the library, because if you had 3 inches worth of punch cards, try getting them back into order. Huh? Well, okay, yes, you'd use a rubber band. That's smart. You number them, or actually, what they usually did was they'd stack them up, and then they'd take a permanent marker and do a diagonal stripe down the side, and then if they got out of order, you could easily get them back. You didn't even have to look at the numbers. You just got it until the stripe was the correct way. Okay, huh? So you like on the side, like imagine on the side of your book, a book, you use like a Sharpie and you make a stripe. Well, if you look at it and the stripe's in the middle, then you know that card should go somewhere in the middle of the stack, right?
It's not exact.
No, it's not perfect, but it's something that you can do quick, and then you can look at the, say, the numbers on the cards or the actual instructions on them to sort it out. Okay. Um, yeah. Anyway, my dad tells me lots of stories about punch cards. Um, he's probably not listening right now. Every now and then, my mom tunes in, which was kind of in the spring. Be like, "Hi, mom." Yeah. So anyway, okay. So this program that we've written is not particularly exotic. All it did was load two numbers into memory and quit. But we can do pretty much anything with this except recursion, um, to do data processing. Okay. In particular, one of the things we could do is we could actually program it to do multiplication, or for that matter, subtraction. So let me go back over to the list of instructions. Um, right? Yeah. Do you see a subtraction operation there? I don't. So how do you do subtraction? Well, yeah. How do you add a negative though? How do you generate the negative? Well, how do you negate a number in two's complement? You flip the bits and add one. Okay. So it won't be the rotate. That actually does something different. So flipping this way and rotating is more like that way. Okay. But we will use rotate because that's actually how you multiply and divide by two in a sense. Um, so yeah, we need to flip all the bits. Well, do you see an instruction that says flip all the bits? No. Okay. And it's not the rotate command, although that would be certainly a good guess. We'll end up using XOR, okay, with a carefully chosen bit pattern of all ones. Because bit by bit, if you do 1 XOR 1, what do you get? Which flipped it. If you do 0 XOR 1, what do you get? Which flipped it. Yeah, okay. So what we'll have to do is think about how can we do operations that for us are a single word, like subtract or multiply, by translating them into the instructions that we actually have.
So to add, to subtract, you have to do
Flip the bits, add 1,
so 3 commands
and then add.
per run.
Yes.
Okay, that sucks.
Them's the breaks, man. It's a basic machine. Okay. Now, that said, real machines do have a subtraction operation. Okay. Even ones in the 60s and 70s did. Um, so this limitation, actually, if I were to modify Brookshire, one thing I would do is instruction number 6, the floating point, I'd get rid of it, and I'd actually make that a subtract. The other thing is that you'll notice that instruction codes 0, D, E, and F are unused, and I would totally use them. Okay, so anyway. All right, well, we will pick up with this fun and exciting discussion on Friday. And be on the lookout for some announcements on Canvas. See if we play.